So which is bigger, 2 to the power of 50 or 19 factorial? The first expression is 2 multiplied by itself 50 times, so if we expand the expression, the product would have 50 terms. The second expression is 19 factorial, which is 19 times 18 times 17 and so on until times 1. That's what the factorial means. This expression has 19 terms in the product, which is significantly less than 50, but almost every term in the product is greater than 2, which is what every term in 2 to the 50 is. So the question is, which expression is bigger overall? The first expression with more terms or the second expression with less terms, but almost every term is larger? So what we can do is take the logarithm of base 2 of both expressions and compare the log of both expressions instead. I'm just going to write it as log, but keep in mind that when I say log from now on, I mean the log of base 2 and not base 10. So if we take log base 2 of 2 to the 50, we just end up with 50. And if we take log base 2 of 19 factorial, we get log of 19 factorial, which is equal to log of 19 times 18 times 17 and so on until times 1. And that's just equal to log of 1 plus log of 2 plus log of 3 and so on until log of 19. So if we compare log of 2 to the power of 50 and log of 19 factorial, the result of this comparison will allow us to infer which of the two original expressions is the greater one. So let's examine the expression log of 1 plus log of 2 plus log of 3 until plus log of 19 to determine how it compares with 50. For example, if the expression is greater than 50, then we can infer that the original 19 factorial expression is greater than 2 to the power of 50. And of course, we should remember that this is all the logarithm of base 2 and not base 10, which is crucial. Here's what we can do with all of these log terms. We can group them up like log of 1, then log of 2 plus log of 3, then log of 4 plus log of 5, and so on until plus log of 7, then log of 8 plus log of 9, plus and so on until log of 15, and in the final group we have log of 16 plus log of 17 until plus log of 19. So what I've done is I've grouped up all the log terms in the sum in this particular way, where each term is assigned a certain group. So now let's consider the lower bound for each group of terms. Log of 1 is equal to 0, since logarithms of any base with an argument of 1 is always equal to 0. But we can say that log of 1 is greater than or equal to 0, which is also true. For the second group, log of 2 plus log of 3, each term in the sum is greater than or equal to 1. This is because log of 2 is equal to 1, since this is a log of base 2, and we can use the fact that log of 3 is greater than log of 2 to infer that log of 3 is also greater than or equal to 1. So we have a sum of two terms where each term is greater than or equal to 1, and this implies that log of 2 plus log of 3 is greater than or equal to 2 times 1, 2 for the number of terms, and 1 for the lower bound for each individual log term, and this equals 2. So log of 2 plus log of 3 is greater than or equal to 2. If we consider the next group, log of 4 plus log of 5, and so on until plus log of 7, we can see that log of 4 is equal to 2, and the rest of the terms in the sum are greater than log of 4. So each individual log term is greater than or equal to 2. Since there are 4 terms in this sum, we can infer that log of 4 plus log of 5, and so on until plus log of 7, is greater than or equal to 4 times 2, which is equal to 8. Similarly, for the next group, we can see that log of 8 is equal to 3, and the rest of the terms in the sum are all greater than log of 8. So this means every term in this sum is greater than or equal to 3. So this means log of 8 plus log of 9 and so on until log of 15 is greater than or equal to 8 times 3, since there are 8 terms in the sum, and each term is greater than or equal to 3, and this is equal to 24. For the last group, I'm going to do something a little different. So log of 16 is equal to 4, so every term that follows it in the sum is greater than or equal to 4. So we can say that log of 16 plus log of 17 and so on until plus log of 19 is greater than or equal to 4 times 4, since there are 4 terms and each term is greater than or equal to 4. But if we consider any term other than log of 16, for instance log of 17, we can see that it's clearly strictly greater than log of 16, which also means it's strictly greater than 4. So actually, the sum is not just greater than or equal to 4 times 4, but it's actually strictly greater than 4 times 4. And this, of course, is another way of saying that this sum has 4 terms where all the terms are at least 4, and there's also at least one term that's strictly greater than 4. So log of 16 plus log of 17 and so on until plus log of 19 is greater than 4 times 4, which equals 16. You'll see why I made this distinction in a second. So what we need to do with all of this is combine all of these inequalities into a single one by summing them all up. Since the left-hand side of all of the inequalities add up to the sum log of 1 plus log of 2 plus log of 3, and so on until log of 19, the left-hand side of the combined inequality should be log of 1 plus log of 2 plus log of 3 until plus log of 19. For the right-hand side, we just need to sum up all the expressions on the right-hand side of each inequality. So we would end up with 0 plus 2 plus 8 plus 24 plus 16. So the sum of log terms is strictly greater than 0 plus 2 plus 8 plus 24 plus 16. The inequality is strictly greater than instead of just greater than or equal to because of the greater than sign in the last inequality. This is using some variation of the property if A is greater than or equal to C and B is greater than D, then A plus B is strictly greater than C plus D, except with more terms. And in fact, this is the property that was implicitly used to infer the strictly greater than relation in the last group, since we used the fact that log of 17 was strictly greater than 4. Okay, so 0 plus 2 plus 8 plus 24 plus 16 is equal to 50. So log of 1 plus log of 2 plus log of 3 until plus log of 19 is strictly greater than 50. If we combine the logarithms, then log of 1 times 2 times 3 and so on until times 19 is strictly greater than 50. And as we found earlier, this expression is just equal to log of 19 factorial, which is greater than 50. And of course, to reverse what we did to the original two expressions we were trying to compare, which was to take the log of base 2 for both expressions, we need to apply the exponential function of base 2 on both sides with log of 19 factorial and 50 as the arguments. If we raise 2 to the power of 19 factorial, we get 19 factorial, since the exponential of base 2 and the log of base 2 cancel out. And if we raise 2 to the power of 50, we get 2 to the power of 50. We can infer that 19 factorial is greater than 2 to the 50 by applying the exponential function of base 2 on both sides, and the inequality sign is preserved because of the property that if n is greater than m, then a to the n is greater than a to the m, provided that the base a is greater than 1. We were trying to compare 19 factorial with 2 to the 50, and using this method, we can conclude that 19 factorial is the greater of the two expressions.